Hello, everyone, and welcome to SPI Health and Safety's webinar. Hope everybody had a great summer, a great vacation if you were able to take some time off. My name is Amélie Leduc. I'm a marketing advisor here at SPI. For those who don't know SPI, basically SPI's mission is to be the single most valuable partner for companies that value health and safety in their work environment. And how we do it is to, sorry about that. Okay, I guess I had the clicker stuck, sorry. That's the joy of live webinars, right? As you can see, we're live. So how we do that is SPI offers training and expertise as well as selling personal protective equipment. We do trainings, we do consulting, we do audits, we do everything for all the category of risks and hazards you see on your screen. Today we're going to tackle a very specific topic in gas detection, which is the kind of sensor that you would need in your sector of activity, basically. So I have the privilege of being accompanied by two experts in the field, and when I say two experts, they both have more than 25 years of experience in the field. So let's start with Guy Baillargeon. Hi Guy, how are you?
Hey, good afternoon, Amélie. I'm doing fine, thank you.
Good. Guy's from Dräger. His title at Dräger is he's the regional sales manager for the federal government and Eastern Quebec. What is it exactly that you do, Guy, at Dräger?
Basically, I do visit end users and work with the channel partner to establish or understand customers' need, and then to provide the proper solution for their needs.
Good. So we're glad to have you on board with us today.
Thank you.
As you may have noticed on your screen, there was a change of plan in terms of whom from SPI was presenting. So we do have the privilege to be with Harry Van Leeuwenkamp. Hi, Harry. How are you?
Good afternoon. I'm doing very well.
Good. Harry has been an advisor, a trainer at SPI for the past 10 years.
For just about 10 years with SPI, but I started working in the field of health and safety back in 1974.
Yeah, it's true. And you're a chemist.
I'm a chemist by trade. That's
yes.
right. And what I do now is I teach courses, I do hazard analysis, I develop prevention programs for anybody that has to do with confined spaces.
All right, so glad to have you on board as well. Just go through a bit of housekeeping before we start. The webinar will last for 60 minutes, which will end with a question period. You do have access to a Q&A box on your console. So throughout the webinar, if you have any questions, feel free to ask us. Obviously, you can ask your question at any time. We'll try to answer it as we go. However, because this is a pretty technical webinar, we may decide while we go through to answer your question at the end. But by all means, ask your questions. For sure, we'll be answering them today or by email if we're unable to get to it. Before we go any further, just want you to understand that we're not going to cover the basis of gas detection. This webinar is really more technical, and we assume that you're so-called regular in gas detection. It's really more of an advanced level webinar on gas detection.
Yeah, I would call this webinar 2.0.
Yes, exactly. So let's start with the objectives for today's webinar, Harry.
Okay, so what we want to have some greater detail in the technology that we use to choose the right sensors. We'll talk a little bit about the technology that's available now to explain why we pick one type of sensor over another. We'll also tell you how these sensors work. This might give you some insight, and talk about different types of interferences, also called cross sensitivities or chemical interferences that we can experience with certain detectors.
Good. I think it's important for us, but for people to understand that the use they require of their gas detectors and the environment that needs to be tested.
Yes, the choice of the measuring principle is decisive for the detection of the gas-related hazards. So each measuring principle has its advantages and its limitations, and we can optimize these for the various groups of gases that we find in your areas. That's why it's important to know what are the gases and vapors that are present in your present workplace. Now you can see on the screen here that although we use this very often in confined spaces, there are other areas that we can be using this for personal monitoring when you're working in various areas of the mill or the plant, for leak detection, and also for when you're working in a specific area that requires gas detection. Generally speaking, we differentiate between three categories of gases. We have oxygen, we have the risk of flammable or explosive gases or contaminants, and we have the risk or presence of toxic contaminants.
So it's actually, let's start with asking our audience if they are aware of the limitations of the technologies found in their own gas detectors. So we'll give you a few seconds. On your screen will pop up the question. You can answer A or B. Yes or no. We'll give you a few seconds, sorry. So are you aware of the limitations of the technologies found in your gas detector? Ten more seconds. That's where we do 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 do
Do do do do.
Yeah. All right. So we have more than 60% of people are confident, but still almost 40% of the people are not aware of the limitations of the technologies.
When I'm out in the field, I find that there's a lot of people put a lot of trust in their detectors, and they don't feel that they really need to know what the technology is behind this. So when it comes to these hazards, the identification is key. So each technology has its own strengths and limits. So we want to be aware of these, and each of this is better for a particular group of gases. It's important to ask, in order to select the most appropriate sensor, which gases and vapors occur in your workplace. In the following table, we have selected a few sectors of activities and the gases that are possible in these sectors.
Yeah.
Now you can see that we've only got a few industries or tasks that are indicated there. We have a much more complete list of this that is available. This is, for example, in the food industry, pharmaceutical, petrochemical, fire, pulp and paper. There's quite a few industries that we have this list available for. One thing we need to clarify is that what we have on here is not exhaustive. In this presentation, we will take some examples from this table and we'll develop these.
And just so you know, we've given you two handouts that you're able to download on your console. One is from Dräger. It's a document on power generation. Basically, they've created a document reflecting on challenges, hazards, and solutions specific to this particular industry. Obviously, Dräger has more such documents for other industries. So if you do want to learn more about yours, by all means, reach out to us and for an expertise call. I will be glad for us to help you out. But also we've given you a handout with this table that you see on your screen, but with all of the other industry or sector that we wanted to share with you. So by all means, download this. If you have any questions regarding it, email us or ask your questions as we go along. So let's have another interactive question in order for us to know the knowledge they have regarding their own industry hazards. So we're asking you folks, do you know the atmospheric hazards that may be present in your industry? Three possible answers today. A, yes, 100%, since there was an evaluation that has been done. B, you do guys have a list, but it may need to be updated. Or three, not really, but you do trust your gas detector. Maybe would like to perform an audit. So we'll give you a few seconds again to answer A, B, or C. If you do see any shortened answers on your screen, don't think it's spelling mistake or it's because we felt lazy to complete the whole sentence. It's more in terms of limitations of web programming. The questions we had limitation in terms of characters, so that's why we add at some point to shorten the answers you see on your screen. So again, a few more seconds to go. Don't be shy. Let us know where you stand. All right. I think we have 33% for each. I think what's important to mention here, folks, is that if you do trust only the gas detector, you may have some surprise at some point.
Exactly.
Yeah.
And it's not something that I'm not surprised by this at all.
No? Okay. Yeah. So you'll see as we go along that maybe the detectors are pretty accurate, but still there's a need for you to be more aware of the environment and so on. Yeah. So let's talk about categories of hazards. Harry?
Okay, so the oxygen is one of the key elements that we want to analyze. So what we normally see is that we have a depletion of oxygen. In some situations, we may actually have an increase in the amount of oxygen. Both of them will present a specific hazard. When it comes to the explosive hazard caused by flammable gases, these are what we say in the jurisdiction is different for each province. So you have to know what your province says about these the permissible levels. And the same thing with the toxicity hazards. There are provincial guidelines that are different in each province. So there may be some differences. So one of the things that we should note is that humans cannot determine the concentration or even sometimes the presence of a certain contaminant in the air. So the gas detector does become your best friend.
Absolutely. And so let's see the 4 types of sensors that we have, because for each gas or family of gases, 1 or more sensor technologies are available, and they will guarantee precision and repeatability of measurements as well.
That's right. So here we can see that electrochemical sensors are by and large the most common of the sensors that were used. They're used for the oxygen for most detectors and also for several toxic gases. Catalytic sensors are used for the flammable explosive gases. This is the most widely used as well. There's another option when it comes to flammable explosive gases. That's the infrared sensors, and it also works well for carbon dioxide. And then we have the PID, the photo ionization device, the sensors for a large array of toxic chemicals, especially volatile organic compounds. So this one here is we see this being used much more in industry. Now, what's important to note is that each of these has its uses, advantages, and disadvantages, depending on the gases present and also your sector of activity.
Absolutely. So let's start with the electrochemical sensor.
Okay, so here we have the most common one, like I was mentioning, and what we have here is a sensor with a solution on the inside and with a porous membrane. The gas passes through by diffusion into the membrane and will react with the electrolyte on the inside. So what we have here is 2 electrodes. We've got some electrodes there, and so when it comes to electrodes, one is a cathode, one is an anode, and me being an old chemist, I have this trick that I learned a long time ago. Use the word panic to determine what is the positive electrode and the negative electrode. Panic stands for positive anode, negative is cathode. So,
well,
a simple trick.
Even if you call yourself an old chemist, I can tell you that we still use acronyms like this to learn.
Right,
I still love those. So.
That's right. So the gas to be measured enters into the chamber, and there's a reaction that takes place at the cathode and the anode, and the current that's created is what creates the signal that we see on the screen. So it is directly converted into a percentage for oxygen or a ppm level for the toxic gases.
Okay.
One thing we should mention here is that these electrodes are normally made out of lead, and lead gets oxidized in air. So this will become depleted over time. So a lifespan of 3 to 24 months is quite common.
Yeah, lead is a common material used in sensor technology, but Dräger, we don't use lead in our oxygen sensor. So this is one of the reasons why our oxygen sensor have been performing very well, and they have an expected life of over 5 years. So this is very important to realize. I would also say that dual electrode, they have some drawback. One of the method is that one of the element is that the concentration, the higher the concentration will generate a higher current, and that current will also generate the lower voltage that will be picked up by the measuring unit of the sensor. And then what happened is that this can even damage the sensor. The fact that we use a third electrode as a reference electrode, it doesn't have any current that passes through it. So this will allow the third electrode to provide like a protection against overcurrent that could be generated, and then providing a more stable and longer life for the sensor itself.
Okay. Toxic gases and vapors detection. Lots of old chemists.
That's right. So on the screen, you can see here NO and NO2, which is often referred to as NOx. And these are often found in combustion byproducts and in various industrial situations. We find them in silos as well. We got chlorine, which is often used in industry or in municipal situations. So it's one of your classic acid gases. Same thing with SO2. It's often found in smelters and petrochemical. It's used as a reducing agent in many chemical industries. We have carbon monoxide, carbon dioxide, which are present in many industrial situations. Ammonia, we've got cyanide, hydrogen chloride, which is often present in industrial situations here. One of the things that we should specify here or mention here is that the sensors come from the sensors are designed so that the anode and the cathode will alter the voltage as they pick up the various gases, and this is what gives you the signal. We can also add filters so that certain cross sensitivities can be eliminated as well, so that we can remove these chemicals to give a much more targeted response.
Okay. Yeah, from a more technical point of view, you've got here another.
That's right. So here we got an example for carbon monoxide. You can see what happens inside the sensor is that there is a chemical reaction that's taking place. So carbon monoxide will react with the oxygen. So it's a forced reaction, which will liberate a bit of hydrogen ions and 2 electrons, and these will migrate towards the cathode. And then at the anode, you'll have the oxygen and the hydrogen that will combine to form oxygen, and this will generate a current. This chemical reaction generates a current, so that we can actually take a measurement, and this is directly proportional to the concentration that we have in the air.
Okay. And what about cross sensitivity, Guy?
Yeah, that's an element that need our attention. We cannot neglect the effect of cross sensitivity. What that means is that when we develop a sensor for a specific gas, but often there could be another gas that will interfere with or will have a response on the sensor itself due to the chemical formula or the family of chemical it is from. It can provide a response on a sensor that it was not developed for. So cross sensitivity will lead to either false positive or it could be a negative reading. A false positive means that it can reinforce or provide a reading on a sensor that doesn't have the target gas is not present, but will provide a response or generate a response on the display. Or negative reading is that the sensor the chemical gas can have the chemical could have an influence on the sensor by providing a negative response on the target sensor itself. So this can cause some disruptive or reading that could be faulty on the display. But by knowing the environment into which the measurement is taking place, at that point we can interpret the result and be more confident in the reading that we do have. Dräger we do provide technical data on the sensor, which we have developed a cross sensitivity table for each of the sensor. Knowing the environment or the sector of activity into which these sensors are being used, we have done tests in lab with other contaminants that could interfere or provide cross interference onto the specific sensor. If you look at the table at this time, this is data for a electrochemical sensor, and as you can see, we've identified two different examples, the acetylene and the hydrogen. And if you look the effect on the sensor itself, the response, and the last two columns, if we look at the acetylene, with the presence of 200 ppm of acetylene, will generate a response of up to 500 ppm on the CO sensor, even if there is no CO presence in the environment. And by the use of a selective filter, in this case, we can reduce the effect of the acetylene to roughly 300 ppm. In the case of the hydrogen, as you can see, with even just a 0.1% volume, which could represent roughly 1000 ppm, it will have an effect on the CO sensor. And even with using a selective filter, we can see that it doesn't have any effect in reducing the impact of the hydrogen itself. So in case of this example, it's very important because sometimes we have developed a specific sensor for a specific application, which we address in the case of the hydrogen onto the electrochemical CO sensor. We have developed a carbon monoxide hydrogen compensated sensor. So in that case, for that specific sensor, I think it is up to 2000 ppm of hydrogen. The electrochemical CO sensor will not provide any response at all. So this was developed for a specific application. One of them is that hydrogen is generated in the battery recharging, and in that case, if you want to monitor in those areas where a battery are being charged, and you can have a response on the CO sensor. So by using the hydrogen compensated sensor, you would have no result, no value or appearing on the display of the unit at lower concentration of hydrogen.
And in terms of advantage and disadvantages to the electrochemical sensor, what are those?
As we didn't mention, but there is a lot of electrochemical sensors that are available depending on the manufacturer. We can have between I would say 6 to about 40 different sensors. So they are low cost because there is a lot of production of the sensors. They are also low cost versus an infrared or a PID sensor if you're looking into some of the VOCs. Some of the disadvantage, one of the effect is in the environment. If the temperature or the humidity are present, they could have an effect when you go from ambient temperature to a low temp environment. The sensor might need to take some time to stabilize.
Okay, and what about the risk of explosions, the two types of sensors, catalytic and infrared?
Okay, yeah, again, those two sensors, for selecting them, it depends on the environment. Both of them will be measuring in the in reference to the lower explosive limit of the reference gas or the measured gas, and also depending on the application, you could have the ability to go in the percent volume range.
Okay. So now let's talk about the catalytic sensor, which I think is the most widely used sensor, right, for detection of flammable gases. Harry, I said Guy, I'm sorry. That's my bad. You should have seen Guy's face. Oh my God. No, it's Harry now, sorry.
Okay, yeah, the catalytic sensors are really very, very widely used. Most of us who have a detector will probably have the catalytic sensors in there. The catalytic sensor works by oxidizing the combustible gases on a catalyst. So this is a filament in there which will burn the combustible gas, and this will produce heat. Now the heat that's produced is compared with another element, what do you call it, a compensator element, and the difference between the two will give us the actual concentration of the gas in lower explosive limit percent. Now this one here, the catalytic sensors will go up to a maximum of 100% of its LEL, so we cannot go beyond that. When These voltages are, the voltages will be created when the element is heated, and the voltages will drop in this filament. And so that's how it's actually measured. The technology is that the hotter the element, the less the voltage will pass through. That increases the resistance. So this goes through a Wheatstone bridge, and then so we get a very accurate signal from this sensor.
Okay. Now it's your turn, Guy.
Okay.
Correction factors.
Yeah, correction factor. This means that first of all, the catalytic sensor is a non-specific sensor, meaning that it will detect all of the combustible gas that are present. What we recommend at our end is that to get the proper reading, or a 1-to-1 ratio reading, is to use the calibration gas that you're most likely, the gas for calibrating the unit, the instrument, that you're most likely encountered to see in the field. So if the area or your environment is of a propane, a risk of a propane leak, at that time, there's nothing that prevents you from, and we would recommend, in fact, for you to calibrate the catalytic sensor with the propane reference gas. Other gas that are available are pentane. Methane is a very common one, depending on the industry and the different environment that you're within. So it is important that you use the proper calibration gas. If you're using a calibration gas, and you're measuring a different gas in the field, different combustible gas, at that time, what we need to apply is a correction factor. So the response of the different gas, let's say the propane gas, if you have calibrated your unit with a methane gas, at that point, the reference between the propane and the methane, there is a correction factor to apply. So it means that with the reading that you will have on your display, if it's 10% LEL, you will have to apply a correction factor that will change that 10% LEL into either 13, 14, or it could be 9, 8, or 7. So there is a correction factor to apply at the time of the measurement. If you know in advance that you are going to be measuring a different gas than what the gas you're using for calibration, at that time in the calibration mode, we would indicate that specificity, the different gas that is going to be measured, and at that time the calculation will be done internally by the instrument. So at that time the reading that you're going to take will be a 1-to-1 ratio, even if you have calibrated with methane and you're measuring propane. On the display, you would have a reading of percent LEL in propane.
I guess as we can see on the chart.
Yeah, the chart indicates, if you look, there's depending on the different gas, they have the display reading. The last column shows that a different contaminant, a different gas will provide or generate a different response on the LEL sensor, and those can be adjusted manually. Adjust manually to the value that you see on the display, or it could be programmed at the time of the calibration, so you don't have any manual input or manual calculation to do at the time of the sampling. So basically, what we recommend is, if possible, to use the target gas that you're most likely to encounter in the field to proceed with your calibration.
Sorry about that. I just saw that the red circles are not aligned. I guess when we transposed the presentation, this moved. So, sorry, my bad. All right, advantages, disadvantages of the catalytic sensors.
Yeah, just in summary there, as we mentioned, is that the CATX are non-specific sensors, so they will pick up a large array of combustible gas. So that's a very good sensor to use. One of the disadvantages is that it does require a minimum of oxygen, like between 8 and 10% volume oxygen in the air, to be able to perform the measuring of the environment. And also, one of the disadvantages is that depending on the environment, due to the nature of the technology, when the gas is burned, if there is a sulfur compound or phosphorus compound in the sample, or silicon-based product, these elements can deposit on the filament, and then it can provide or generate a much lower, longer response time to the sensor. So this is a disadvantage. And at that point, you would need to, this is why most of the manufacturers recommend to calibrate the catalytic sensor at a greater frequency or more frequently, if I could say so.
Okay. So let's continue with the infrared sensor, Harry.
So we were talking about flammable gases. So here we have an infrared sensor, which is also used for detecting flammable gases, and it can also be used for carbon dioxide as well. And one of the important advantages of this is that it will measure the flammable gas even at very low oxygen concentrations, or even at no oxygen in the gas. And it can be actually measuring not only in percent of the LEL, but we could also have it set up for percent of its actual volume by volume concentration. So this is a sensor that's much less used in industry, and but it may have some important advantages for some people.
Okay.
So the technology that's used in here is it's an infrared light. So this gives a certain light spectrum. The infrared sensors exploit the principle that the molecules, different molecules, absorb light at different wavelengths. The sensor contains this infrared light source. The infrared radiation emitted from it is not absorbed by common gases such as oxygen and nitrogen, which is a pretty good advantage. The double detector inside the sensor measures the reduction of infrared radiation as it's absorbed by the gas. So the difference between what is emitted and what is picked up gives you the direct reading. These sensors have several major advantages over catalytic sensors. They offer an extremely fast response, usually less than 10 seconds. There is a minimal maintenance that is required, and they are ultra simplified controls, thanks to the self-control function managed by the modern microprocessor. They are also resistant to the various poisons or these interfering chemicals such as phosphorus, sulfur, and silicone, so that affect catalytic sensors. So that we don't have those problems with the infrared sensors. And the fact that they can work with zero oxygen can be an advantage to many applications. They also can work at a various range of temperature, pressure, and humidity. So that's another good advantage for this type of sensor.
Definitely. Oh, the correction factor is...
Yeah, correction factor, again, it's in terms of the fact that the sensor is a non-specific. So same thing, we recommend that you use the calibration gas that you're most likely, the gas that you're most likely encountered to monitor or see in the field. Compared to the catalytic detection, the response factor to the different gases is not linear. As you can see on the slides, the methane, the one that goes from bottom left to top right, this is as a linear response. But some of the other gas, like if you look on the red line, the propane is not a straight line. It has a curve in it. So what we recommend is that you can calibrate the same sensor with different reference gas, and then store that in the memory. And at the time you need to do the measuring, you can switch from one to the other to go to the specific gas that you're monitoring. And then at that point, that would increase the reliability of the measurement that you will have on the display. So you need to be careful that some in the industry, there are some infrared sensor for catalytic, for explosive gas that are specific to that they are specified to be specific for a target, dedicated gas, if I can say so. But in that case, you need to be careful, because this is probably an indication that the response to other combustible gas might not be that accurate. So you need to check with the manufacturer of the sensor.
Okay, we've talked about the advantages, a bit disadvantages, but if you were to resume, Harry,
yeah,
or...
You can see on the screen here several advantages there, and I think the one that probably would grab your attention is the longer life because it's resistant to such poisons, we have a longer life of the sensor. So it's a pretty good advantage. There are a few disadvantages, but especially the higher cost might be dissuade some people. But I think the advantages far outweigh the disadvantages.
Okay. When talking about catalytic versus infrared sensors, Guy?
Yeah, what could help in selecting one versus the other? A couple of elements that could be considered. Basically, on the environment itself, the temperature and the humidity that you are facing, or presence of humidity. Sometimes this will dictate to go with one sensor over the other one. The catalytic sensor have been in use for much longer time. They have a better, longer history, I should say, than the infrared. So it has it's a less expensive, but the life expectancy is shortened depending on the environment, as we mentioned, some of the poison gas that could affect the sensor itself. On the other end, the infrared sensor is more expensive at this time, but it is a more recent technology. So over the next few years, there's a good chance that the production will increase and the technology will make it that we can have a lower cost for the infrared sensor. The infrared sensor has the ability also to work in oxygen deficient environment. So this is very important depending on the industry you are with or the application, that measuring combustible gas, if there is a chance that within the process you ended up with no reading on the display, so that could be pretty dangerous or hazardous. So the infrared in those cases where you have a risk of low oxygen might be or would be your best option.
Okay, interesting. So moving on with the last but not the least, Harry, we've talked about catalytic, electrochemical, and we've talked about infrared. Now let's talk
the
about
last one, the PID. So the PID, the photo ionization detector. It's not as well known, but we're seeing it used much more now. It's a specialized sensor that is known as a broad range sensor and is not specific to one gas. It's used for all kinds of toxic gases, especially volatile organic compounds. So when you have a lot of volatile organic compounds, whether it be because of the nature of the industry or the nature of the work being performed, this might be a very good option to have. And we'll give you readings in either parts per billion or several thousand parts per million. And it will give, and this will be referenced to, of course, the threshold limit value of the gas that you're dealing with. Common gases or solvents are benzene, acetone, styrene, arsine, butadiene. These are common industrial gases, but there's quite a large selection of solvents and gases that can be used, or volatile organic compounds, that this sensor will be used for. One thing to note is that all these solvents and volatile organic compounds are usually far more toxic than they are inflammable. So it's very interesting to have a PID so that we know what toxicity level is before we get to the percent range of the LEL.
Very good point.
So again, how does it work?
Okay, so when it comes down to the technology, we have a little lamp in there, a little ultraviolet lamp, and which will create a change in the chemical. So we create ions in there, and they will get picked up either by the anode or the cathode. And so here we have that acronym that I like to use. The positive is anode, that's right, negative is cathode. The ultraviolet lamp will energize this compound that's in there and will generate a current. So this current will be directly proportional to the concentration that we have inside that inside the sensor and the gas that you have. It's important to note that the ionization potential for each gas is known, and the energy produced by the lamp must be greater than the ionization potential of those gases. So we'll see later on, we'll see in the next slide, a certain choice of lamps with different electron volts, different energies that are available in these lamps. So The 9.8 doesn't have a very broad range of volatile organic compounds or toxic chemicals, but it's the one that has the highest lifespan. It's the most stable one. The most common one used is the 10.6, and it has a very broad spectrum of gases and volatile organic compounds. And for example, we use it for measuring the various alcohols, acetone or other ketones, WD-40 brake cleaner, paint solvents, aromatic compounds, aliphatic compounds. So it's a very much used sensor, the 10.6, and it has a pretty stable lifespan of 2 to 3 years. Then if you need a greater range, well, you got the 11.7. The disadvantage being that it's got only a lifespan of a few hundred hours. And there's also some serious interferences from carbon dioxide or from humidity. Oxygen level can cause certain interferences. So these are the choices. Like I said, the 10.6 is the most common one used.
Okay, and in terms of calibration and response factors for this types of...
So normally what we use to calibrate is the isobutylene. So this is a separate cylinder, so a second cylinder that we have to use for calibration. So the different sensitivities of these volatile organic compounds will create a response factor of less than 1 or greater than 1. So there are some correction factors to apply, so that we should be aware of this when we're detecting these gases. So these calibration curves can be requested from the manufacturer.
Okay, Guy, it's for your time to review the response factor.
Yeah, on the table, as you can see, on the column in the middle there, ionization energy. This is specific to each contaminant, and you can get that data from chemistry book or chemical book. It's universal. I mean, it's the same value all over the world. What is different is the response factor, which is specific to the manufacturer of the equipment, the lamp itself. So this is the response factor will have an effect, or will be needed to apply to the direct reading of the measurement or the gas. So in the example, we in the table we have identified or mentioned the chemical that have a response factor lower than 10.6. So all of these elements can be picked up by the 10.6 electron volt lamp. And as you can see, the ionization varies from one substance to the other. So if we go with the reference cal gas, which is the isobutylene, we see that the response factor on the last column varies from one element to the other. As we can see, let's say for benzene, the top one that is circle, the response factor would be about half by 0.5. So we will need to apply that correction factor to the displayed value on the reading. On the other end, for the propanol, the value, the response factor is 4. So the value that would be displayed on the unit on the screen would need to be multiplied by 4 to have the exact value that we are facing or that is present in the environment. So as I mentioned, the response factor, this is the key element that need to be verified with the manufacturer of the equipment, because it can vary, it will vary from one manufacturer to the other.
Absolutely, that's a good point. And when talking about advantages and disadvantages for this particular sensor, Guy?
Okay, the PID offers a wide range in detection because it can pick up a lot of the contaminant. It's not specific to a sensor. Very fast response time. And what can be some kind of disadvantage is that it will not differentiate. As I said, it's non-specific. So if you have multiple VOC or contaminant at the same time, you will not be able to differentiate between one or the other.
Perfect. So when people have to choose the sensor according to their sectors of activity. Guy,
Okay.
or Harry.
Harry.
Again.
My turn.
Sorry.
Yeah, so here depending on your sector of activity, we're going to be able to tailor the gas detector. We'll have either electrochemical sensors in there. We may have some catalytic, or we'll choose the infrared sensors. And in many cases now, we're going to be seeing people who want to have this PID in there, depending on what they have in terms of gases there, and also what we have in terms of cross interference or cross sensitivities.
It's important to know as well, if you need help choosing the right sensor according to your sector of activity, SPI and Dräger can do a joint call or a joint visit to make sure that they analyze, basically do an audit and help you out directly. So that's the kind of service that we do in partnership with Dräger. Time for us to ask you, so far, based on the information that you've learned, would you consider reevaluating your detector needs? So for possible answers for you today, is it A, yes, you'd like to have an evaluation of your contaminant sources? B, you'd like to have an industrial hygienist to evaluate your environment? C, you'd like to review your equipment or even have a demonstration of available products and technologies in your particular industry? Or no, you're confident that you're all set. So we'll give you a few seconds. Again, be nice with the types of writing there that's there. I had to limit the amount of characters in the question. Ten more seconds. Don't be shy, just let her know where you stand. All right, thank you very much, everybody. Now, well, Guy, Dräger has created several resources. You're going to talk to us about a couple for now.
Yeah, quickly,
The
a
handbook.
couple of reference or resource guide that we offer either directly on the website or in a electronic format. We do have a Draeger sensor handbook that will provide all the information on the sensor and the instrument within the Draeger gas detection portfolio, which is in constant evolution. Every time we try to improve durability, reliability, or even cost of ownership for our different products. So in that handbook, there is all the technical information about the sensors, the response time, the effect of temperature, humidity, and also, as we mentioned earlier, the table with the cross sensitivity. Another one that is also very widely used is the Draeger Voice, which is a database easy to access on the website at draeger.com/voice. You just need to key in the chemical name, or even more commonly the CAS number, and that will provide you with all the information in terms of availability for gas detection. We've discussed today about the electronic portable monitor, but there could be all other means of detection. It could be the Draeger tube in the calorimetric tubes. There's a couple of other technology that could also be available within Draeger. Also, it will provide you information on the respiratory protection associated with that specific contaminant.
The pinwheel, I called.
Yeah, the pinwheel. What we've discussed today about some of the technology within the Draeger, we are very proud that the art of the gas monitor is the sensor, and the Draeger is very technically oriented research and development. And just to mention that our first oxygen sensor have been developed almost 50 years ago. So we like to say that technology, we bring a new development, new technology into a technology for life. Just for note over here, Draeger filed roughly, or an average, one patent per week. Request for patent every week. So we do a lot of development on new technology. just to finalize on that, to confirm that, is that we just came out early on this year with a brand new unit, X-pid, which combines two technology. One of them we already discussed today, the photoionization technology, the PID, which is we do have a PID sensor in the X-pid, but we have also included a technology that so far has been used only in laboratory because of its larger scale. It's a gas chromatograph. So the X-pid 9500 combines both those two technology, providing the ability to detect some of the contaminant, basically, namely the VOCs, but also to analyze them and provide a reading or a listing of the different elements present in the environment. So this is just to show that we're developing new technology and new instrument on a regular basis. So if you want to have, if you're interested in that instrument, there is possibility, just contact the SPI, and we will be more than glad to make appointments to do a demonstration of the unit at your facility.
Absolutely. You actually have my email right here. So if you have any question, or if you have you're in need of support, feel free to email me. I'll make sure I contact Guy and Harry to respond. So it's now the question period. So if you have any question as specific as you want, feel free to send them over. As I wait for your question, just want to give you the heads up. Once the webinar is done, we'll be sending you a survey, a quick survey, which is very important for us to collect the data, see if you liked it, what you didn't, what kind of topics you would like us to address in the future. This is, I like to call it a gold mine for us, because it gives us the opportunity to tackle subjects that are pertinent to your reality. So feel free. Time is running by. So what I'm going to do is, for the ones who have answered, ask the questions, will respond directly to you. But first of all, well, thank you, Guy. Thank you, Harry,
You're very
for
welcome.
your expertise. Your
always a pleasure.
Yes.
For your sense of humor with the old chemist that I love. I hope the presentation met your expectations. Again, the survey. Also, I encourage you to visit our website, our social media, as well as our blog. You'll get a lot of information, and we will send the replay link to you guys tomorrow. So if you missed some information, you want to listen to it again, no problems. And also, we are sending you a blog article which has summarized the information we mentioned today on the 4 types of sensors. So again, should you need any information, contact me. Otherwise, on behalf of SPI and Dräger, have a wonderful afternoon, but most importantly, be safe.
Have a great day. Bye,
everybody.
Thank you.